My name is Kaito Shibutani from Kogaku University. Today I'd like to talk about evaluation of disaster information sharing system in various situations. At the beginning, I'll talk about research background. In large-scale disasters such as earthquakes, communication infrastructures can be damaged. DTN achieves end-to-end communication in such a poor communication environment by adopting the carry-forward method. We have proposed a disaster information sharing system based on DTN architecture for situations where the usual communication channels are unavailable. Our proposed system uses media storage devices such as USB memory sticks as relay nodes for DTN. Next, let me talk about the outline of our proposed system. Our proposed system collects and distributes disaster information by using evacuation centers in offline areas where communication is disrupted as communication nodes. Communication between nodes is realized by manually carrying communication media such as USB memory sticks or smartphones. These communication media are referred as a portable storage device hereafter. At a node, evacuees post contents such as safety information or disaster information to the system. We assume video message of 1 minute for these contents each term of tampering resistance and convenience. Posted contents are stored in a portable storage device at evacuation center and is manually transported to other evacuation centers. This enables virtual communication between nodes. Since we assume that the evacuees will be evacuating autonomously and immediately after disaster, the evacuation center to which the content addresses belong is unknown. Therefore, in order to allow the addresses to view the content addressed to them, the system must distribute all the contents to as many nodes as possible. The purpose of the proposed system is to distribute all the contents posted by evacuees to as many nodes as possible. In order to achieve this purpose, there are some constraints due to the characteristics of the system. The first constraint is that communication between nodes is high delay. The second constraint is that the receiving node of a portable storage is unknown at the time of sending it. These constraints arise because the transportation of a portable storage device relies on the autonomous movement of evacuees. The third constraint is a limit on the number of contents that can be sent at one time due to the capacity limitations of portable storage device. In this system, it's important to diffuse contents efficiently under these constraints. Next, let me talk about the problem formulation. The overall purpose of this system is to diffuse all contents to all nodes. Therefore, we set diffusivity defined by this equation as the objective function of this study. Diffusivity is an index showing a ratio of nodes that have distributed all the posted contents. That is the purpose of this study is to maximize the value of diffusivity at each time. In order to maximize the diffusivity, an algorithm that selects which contents are stored on the portable storage device as it's sent from a node is important. This system realizes efficient diffusion by assigning priority to contents and selecting contents based on priorities. In our previous work, we proposed this content selection method. Next, let me talk about the purpose of this study. In our previous work, we proposed a content selection method to achieve efficient content diffusion on the system. However, in the previous simulations, only one network and a simple model were used for the evaluation, and real disaster characteristics such as geographical requirements were insufficiently considered. In this presentation, we evaluate the performance of the proposed method in various situations. Specifically through simulations using several networks with different node placements and unique transportation model. We verify the effects of the number of nodes, node density, or communication frequency between nodes on the performance. Next, I'll explain the content selection method proposed in our previous work. In this presentation, we hereafter refer to this content selection method as the proposed method. The proposed method calculates the priority of contents by these three steps. First, I'll explain step 1, estimation of transportation frequency. Here, S is the sending node of a portable storage device. Tc is the time at which the portable storage device is sent from node S. And C0 is the content for which node S calculates the priority. Also, large N hat is a node set of other nodes in the network observed by node S at time Tc. In the initial state of a node, each node has not observed information about other nodes in the network. Observes information in the network only through the transportation of portable storage device. First, node S predicts the unknown receiving node of a portable storage device at time of transmission by estimating the transport frequency between nodes. Here, K is the number of nodes observed by node S. The transportation of portable storage devices can be regarded as K events that indicates which node is its sender when node S receives a single portable storage device. The occurrence probabilities, these K events are indicated by the vector mu. That is, each vector component is the probability that each node sends a portable storage device received by node S. In this study, we assume that the probabilities that each node is the sender of a portable storage device are similar to the probabilities that each node is the receiver of a portable storage device sent by node S. If these probability distributions are very similar, node S can predict a receiving node of a portable storage device it sends by calculating the vector mu. The proposed method uses Bayesian inference to calculate the vector mu. Next, I'll explain the likelihood and the priority distribution for use in Bayesian inference. The proposed method uses the multinomial distribution as the likelihood. This is because the result of each trial is k, and m independent trials are performed. The random variable m indicates the number of times each event is observed over the m trials. That is, each vector component is the number of times node S received portable storage device sent by that node. Next, the proposed method uses a uniform distribution as a non-informative prior used in the first Bayesian update. The proposed method uses the posterior distribution obtained at the previous update as a prior for subsequent Bayesian updates. A posterior distribution is calculated by Bayesian inference using the likelihood and the prior distribution. Each time node S receives a portable storage device, it updates the posterior distribution using Bayesian inference. Whereas when node S sends a portable storage device, node S estimates the parameter mu hat from the posterior distribution using map estimation. Map estimation is a point estimation method that calculates a parameter that maximizes the probability density of the posterior distribution. The vector mu hat indicates the probabilities that the portable storage device sent from node S will arrive at each observed node. That is, the vector mu hat is the transportation frequency information between node S and other nodes, and is represented by this vector q. Next, I'll explain step 2, estimation of content diffusivity. Each node of this system has a content database that manages which contents are already held by nodes in the network. Node S refers to content database and checks whether each observed node already has content C0. Here EI is the holding state of the content C0 at node I. EI is 1 when the content is held. EI is 0 when the content is not held. Next, node S uses the content holding status to generate a vector E shown in this equation. This vector E is an estimated diffusion information of content C0 in the network. For example, there is a network as this figure, and the yellow nodes hold a content. In this case, the vector E is as follows. Each vector components are each node's content holding state. However, communication between nodes in this system has a high delay. Therefore, the information observed by each node isn't the latest. Finally, I'll explain step 3 calculation of content priority. A priority is calculated by this equation using the transportation frequency information obtained in step 1 and the diffusion rate information obtained in step 2. Large P is a priority of content C0 at time tc calculated by node S. The proposed method assigns higher priority to the content that has a high probability of receiving a portable storage device and a low diffusion rate in the network. Node S calculates a priority for all the contents it holds using this procedure. The priority is a diffusion expectation value that indicates how much the content contributes to maximizing the objective function. Node S selects the contents to store in a portable storage device in order of the priorities under the capacity constraint. This is the content selection method we proposed in our previous work. Next, let me talk about the evaluation. In order to verify the effectiveness of the proposed method, we evaluated the proposed method using a simulator. The purpose of this evaluation is to verify the effect of node placement and heterogeneous transportation frequency between nodes on performance by using several networks and a unique transportation model. In this evaluation, we used the 4 evacuation center locations shown in these figures. By using networks that reflect these evacuation center locations, we verify the influence of node placement. Next, I'll explain the simulation conditions. The number of contents posted per node is 400. This is because we assume the number of evacuees per node is about 200 and each evacuee will post 2 content. We assume that the contents are 1-minute video message, so the content size is set to 100 MB. The number of portable storage devices sent per node is 50. The capacity of portable storage device is 20 GB to 100 GB. Both sending portable storage device and posting contents follow Poisson distribution. The simulation period is 5,000 minutes, because it takes about 3 days to restore communication infrastructures. Next, I'll explain a transportation model of portable storage device which determines the difference in a transport frequency between nodes. As mentioned above, the proposed method assumes that the two-way transport frequency between two nodes is symmetrical. Therefore, we used a model in which the two-way transport frequency is heterogeneous, evaluated the influence of symmetry assumptions on performance in the proposed method. In the simulations as shown in this figure, we use a model in which portable storage devices sent by a node are received with high frequency by nodes located in the east, and with low frequency by nodes located in the west. This allows the performance of the proposed method to be evaluated in a situation where the two-way transportation frequency between nodes is asymmetric. Specifically, this transportation model calculates the weight which determines the difference of transport frequency by this equation. Here we use evacuation center locations in Japan for evaluation, so the node is located on the east side as longitude increases. This function returns a larger value when distance between nodes is closer to 0. That is when calculating a weight for the neighboring nodes of the sending node. In addition, this model doubles these weights for the node on the east side, so portable storage devices are frequently transported to nodes located on the east side and neighboring nodes of the sending node. Such the model, which is frequently transported eastward in the network, would be unrealistic, but we use it here to evaluate the influence of the heterogeneity of the two-way transportation frequency on performance. Next, let me talk about the comparison methods used in the simulations. First, random method and MRP method are used as simple methods. Random method calculates a priority based on a uniform random number. That is, random method randomly selects the contents to be stored on the portable storage device under capacity constraint. MRP method calculates a priority based on the contents registration time. This method assigns a priority to the contents with short time elapsed from registration and gives priority to fresh content. Next, I'll explain the conventional LED method. LED method calculates the priority based on the diffusion rate information of each content. The purpose of this study is to maximize the diffusivity, which is the objective function at each time. Therefore, LED method gives priority to contents with low estimated diffusion rate in the network. Unlike the proposed method, LED method uses only content diffusion information for priority calculation. Here is a list of the information that each method used to calculate the priority. Also, we use diffusivity, which is the objective function, as an evaluation index. Each method is a higher performance if diffusivity is closer to 1 indicates. Next, let me talk about the simulation results. Please look at these figures. These figures show the simulation results using each network. The horizontal axis shows the capacity of a portable storage device, and the vertical axis shows the diffusivity. First, in all figures, we can see that the diffusivity increased as the capacity of a portable storage device increased, and the performance of the proposed method was the best among all methods. From these results, we can see that the proposed method is more efficient than the comparison methods for all the capacities of a portable storage device. Also, these results demonstrate that the proposed method can diffuse the contents more efficiently than other methods without being affected by the network, such as the number of nodes or node density. Next, we compare the proposed method with random and MRP method. These figures are simulation results that emphasize the proposed method, random method, and MRP method. The performance of random and MRP method is considerably lower than that of the proposed method in all figures. In the upper right and lower left figures, we can see that the performance of MRP method is almost identical to that of the proposed method when the capacity of a portable storage device is large. But this is because the content held by each node are saturated. This result demonstrates that simple approaches cannot improve the diffusivity on the proposed system, and that approaches such as the proposed method are necessary. Next, we compare the proposed method with LED method. These figures are simulation results that emphasize the proposed method and LED method. This result demonstrates that the proposed method has the potential to improve the diffusivity without decreasing the performance even when the three-way transportation frequency between nodes is heterogeneous. In contrast, since the LED method does not consider the transportation frequency in the priority calculation, the performance will decrease. From the above results, we showed that the proposed method can guarantee a better performance than the comparison methods regardless of node placement in the network and the capacity of portable storage device. In addition, also the proposed method assumes that the two-way transportation frequency between nodes is homogeneous. It can deliver a good performance even when it's heterogeneous. Now let me summarize my presentation. In this presentation, we evaluated the content selection method proposed in the previous work in various situations. Through simulations, we showed that the proposed method guaranteed a good performance without being affected by the number of nodes, node density, or transportation frequency. However, in these simulations, we assumed that the number of contents and the number of sent portable storage devices per node are uniform, and this heterogeneity should also be considered in real disasters. Performance evaluation of the proposed method under more realistic conditions is future work. This brings me to the end of my presentation. Thank you for your attention.